Uh, Hi everyone. So this sessions we would like to explain about the RF communications using software-defined radio. So hope you enjoy these sessions. So first, before going to the demonstrations, we have to know what is software-defined radio. As per the Wireless Innovations Forum, they define software-defined radio as it's a radio in which some or all the physical layer functionalities are software defined. Means software defined radio refers to a technology wherein software modules running on a generic hardware platform that are used to implement the radio functionalities. So, what are the hardware setup we used for these applications? So, first, USRP B200. It's a entry level software defined radio device which have single trans receiver, one transmit or receiver channel, and other is the receiver channel, and which having the frequency range 70 megahertz to 6 gigahertz, and one steel enclosure for USRP B200, and then vertical antenna VRT 2450, and which is dual band, and the range is 2.4 to 2.5 gigahertz and 4.9 to 5.9 gigahertz. So first we have to explain what is the block diagram, what inside the USRP B210 or B200. So basically USRP B200 having main two components. One is the Spartan 6 FPGA device, and that is connected with the USD FPGA that we'll use to control streaming and synchronizations, and which also connected to DDC and DUC converter. And second part is the analog to analog device component, that is AD9364 RFIC, and which directly connected to the RF front end, that TRX or the RX2. And this device having the USB 3.0 controller, so you can easily connect it with your computer or any USB 3.0 port. So that is the explanations for the each block, each particular chip inside this USRP B200. So inside the Xilinx Spartan 6, that is XC6S LX75, that is the FPGA IC, and then analog device AD9364, that is RFIC, and then that has been connected to the RF front end, where is the two SMA connector is there. One is for the TX/RX, which can be used as a transmitter as well as receiver, and second one is the receiver or RX2 channel. Okay, and the USB 3.0 controller is also available. So this is the basic block or functionalities of the USRP B200 devices. Then what is the key features of the USRP B200? And firstly, it's a fully integrated USRP device with the continuous RF coverage and frequency range from 70 megahertz to 6 gigahertz. And it can function as a full duplex operations up to 56 megahertz with the real-time bandwidth. And for the programming support, we can say USRP B200 can support many platforms like LabVIEW, MATLAB. Along with that, some free tools or the open software like GNU Radio, OpenBTS, and Python and all. So this is the key features or highlights of the USRP 200. And now in our first applications, we are going to use basically LabVIEW programming environment for first programming part. So what are the required software or required tools we have already installed in our system? First, LabVIEW, that is the integrated development programming environment. Then secondly, LabVIEW modulations toolkit, and a USRP driver and UHD or hardware driver for USRP for meters. Now, as per the every programming tools or programming language, so USRP instrument driver also having some programming flow, as this is the basically used as a transceiver. So this having two flow, one is the transmit signal flow, and another one is the receiver signal flow. We'll explain one by one. So first, transmit signal programming flow. So transmit signal means first we have to put that OpenTX sessions. So OpenTX sessions, which will be specified as a transmitter device name, like what is our name of these USRP devices. Then secondly, we have to configure those signal. Configure means we have to specify the IQ rate, carrier frequency, gain, and active antenna. And secondly, then we have to write the data, write the transmit signal. So which signal we have to transmit, that signal we have to specify, that is baseband signal, that transmit data. And then finally, we have to close the USRP session. So this is the transmit signal programming flow. So here it's clearly mentioned what are the different meanings of the different block or functionalities. Then what is the receive signal programming flow? So receive signal programming flow, first two blocks is almost common or same. That is open RX sessions where you have to define the receiver device, USRP device name, then configure the signal like IQ rate, carrier frequency, gain, and active receiver antenna. Then we have to initialize the device, then fetch the RX data, which has been received at the RX antenna, RF end. Then we have to analyze and present the data. Then after that, abort the executions and close the session. So these are the functioning programming library block for the programming receiver end. These are the different meanings, different block functionalities. These sessions are already mentioned. Now we have to go into our hardware demonstrations first. We have to implement one continuous transmit and receive of the IQ in phase and quadrature signal. Let's start that. So we have to open the USRP device, and inside the LabVIEW, first is the device name, and we have to identify the device name inside the NI USRP configurations utility, where I can see my USRP device name is my B200. So that has been specified here, and IQ rate 200 kilo, and then carrier frequency 915 megahertz, and transmit slash receive is my active antenna. Now we have to run this program. Now the program has been running. Now again we have to go to the receiver end to see the functionalities. First I have to explain like what exactly inside the block diagram panel. So inside the block diagram you can see, so first is the open transmit sessions. Inside the open transmit there is a device name I have to specify. Then USRP configure signal where the IQ rate, carrier frequency, gain, and active antenna we have defined. Then inside while loop we have put the USRP write transmit data, and which data will be transmit at the transmitter end. Here we have taken the two waveform. One is the sinusoidal waveform, other one is also sinusoidal waveform with the phase difference 90 degree. That means there is a cosine signal. So one is sine, another is the cosine signal. We have specified here. Okay. So now we have put the get waveform component like dt and then we put some build the waveform, means real and imaginary part. We are merging both the things in a complex real to imaginary converter. Okay, so that is our IQ data, and which IQ data we are sending to the transmitter end. Okay, so that is our explanations of the transmitter signal, and that is a spectral measurement where we have seen the spectrum of this graph. This is the time domain, this is the frequency domain graph of our signal. So that is the transmitter part, and in later part we are explaining about the receiver sections. Now at the receiver end, we have to first open the USRP device utility to identify the device name. In our case, my USRP ID is my B200 underscore one. We need to just copy this one and put inside the device name sections. And IQ rate same like 200k and carrier frequency 915 megahertz. And for receiver active antenna, this is the receiver antenna. Okay, RX2. Now we have to run. In our case, transmitter signal already running. Need to run this one. we could see the what are the signal we generated from the transmitter end. That same signal has been received from the next channel. So this red color LED that defined as a transmitter of the signal, and this green color means it's a receiver end of the signal. Okay, so for the demonstrations for continuous IQ transmit and receiver. Now, in this program, there is two waveform. One is the in phase is showing as a blue color, and quadrature showing as a red color graph. And in the downwards, it's showing the frequency spectrum. We go to the block diagram part of this particular programming. Here you can see first we have decided that this is the USRP open sessions, and this is the configure of the signal. Then we have initialize. Then this is the paste the RX data, how we have explained previous slide. And after paste the data, this is your power spectrum density display frequency plot, and this is the IQ data in the time domain. And then finally we have to abort this USRP and close this session. So that's all for the receiver end programming. So thank you for listening. Hope you enjoyed this session. Thank you. Hi everyone. As we mentioned earlier, our USRP B200 device is compatible with other open source platform like OpenBTS and GNU Radio. So in these sessions, we will demonstrate like how the USRP B200 will communicate with the GNU Radio companion tool. Okay, so for that, we need to go to the search options and type the GNU Radio companion. So when the GNU Radio companion tool will open, we can find there is two blocks. One is called options and second one is called the variable. It's already created in these sections, right? And now in the right side, we can find all the different functionalities and blocks, okay? So inside the UHD part, we can find UHD USRP source block. So just drag and drop this USRP source options, okay? So inside the USRP source, so first we need to change this variable, which variable ID was sample underscore rate. That is the by default value. Now we need to change it. What will be our sampling value? So sampling value by default it is 32 kilohertz. Now we need to change it to the 2 megahertz range. So how to write 2 megahertz? 2 to the power 2 into 10 to the power 6. So to the power will be defined as double asterisk mark. Okay. So now we need to click apply and OK. So now UHD USRP source functionalities we need to change. Okay. So inside USRP source functionality sections, there is one called RF sections. We can find the center frequency. Inside the center frequency, which by default value is the 0, we need to change as a freq. Freq is our variable which we already defined and whose value is the 2 megahertz range. Okay. And AGC, which is by default positions, now we need to enable it. And there is a channel, we need to decide the which channel we have connected. In our case, we have connected with the RX2 channel. So just click apply and click OK. And next part will be, we need to take a variable called QTGUI range, which will decide some range, enter range of our frequency. So just type QTGUI range. Just drag and drop for this part. And if we double click these sections, so default value, start value and stop value, that we need to change. So here range means we have to define the FM frequency range. Okay. So in our cases, so suppose we are starting from 87 megahertz. So 87 into 10 to the power 6. So that is our start value. So start value also will be the same, and the stop value, suppose we are want to measure up to 107 megahertz range. So it's 107 into 10 to the power 6. Okay, and step, for each step will be 200 kilohertz. So 200 kilohertz will be the frequency gap between each channels. So suppose 210 to the power 3. Now click apply and OK. So now this QT GUI range has been completed. And now we need to put, there is two block we need to put, one for the QT GUI for time sync and frequency sync options. So there is two GUI sync options we have taken. So inside the time sync options, we need to enable the auto scale. So just auto scale, we need to click yes, apply and OK. Inside the frequency sync, we need to change the center frequency. With center frequency by default it was 0. Now we need to change as our variable name FREQ. Okay, and then click apply and OK. Now we need to draw this or interconnect those blocks. So first UHD USRP source, that will be connected with sync and source functionalities. So how to connect? So just take the mouse pointer over here and leave it where you need to connect. At the same time, this output signal will be connected to the frequency sync part also. Okay. So now, and this QT GUI range we need to put on the above sections. Okay. Only one thing we need to change, that variable name, that is the sampling rate we have decided, this is 2 megahertz, and QT GUI range, that variable range name will be FREQ. Okay, click OK and apply. So now up to this part has been completed. Now we need to take some audio sync channel, which will be the receiver of the audio signal. So just take audio sync options. So if we double click, take the sampling rate at 48 kilohertz. Okay, and now apply and OK. So in our next case, we need to take a receiver, WVFM receiver or WVFM receive. So this block we have taken. Now this signal out will be connected to the audio sync part. Now we need to change the properties of the WBFM receive sections. Okay, so here is the quadrature rate. We need to decide it, which will be 48,000 multiply 4, and audio decimations, that will be 4. Now click apply and OK. And now we need to take another block which is called rational resampler. Take this rational resampler and double click to change the properties. So interpolations will be 12, decimations value will be 125, and then click apply and OK. Now how to connect those part? So this WBFM and audio sync and rational resampler all will be interconnected. Okay, and from USRP source output we need to connect it to the input of the rational resampler. So now our program and flow graph has been ready. Now we need to run this program. So in our cases, just if we run this program, before run we need to save it. Suppose we are saving test FM radio station. Just save it. So now we can see, okay, one part has been error, one syntax error has been came for the options. So for this part we need to mention the title. We could put the title and name. There is no space between the name of this program. So suppose test FM, test underscore FM, that is our name of this program. Just apply and OK. Here also we are using test underscore FM. Apply and OK. File and save it. We are mentioning test underscore 12. So now my program is ready. So if we run this program, now we can see they execute the flow. So this is the frequency and this is the time and this is the frequency graph. Is already showing. Here is the channel. So suppose we are changing the channel like 100 megahertz, or if we just drag and drop. If we have some known frequency of our radio station, we can easily put, suppose we want to change to 98.3. So just type the value. Suppose we need to change the 100 megahertz range or 100.1. So this is the local channel. Okay. So different channel vector we can change. So in this way, so if we stop this program, now the audio signal has been stopped from the USRP devices. So in this way we can implement different frequency modulator, demodulator, as well as broadcasting some audio signal or frequency receiver, FM stations, anything we can develop inside the GNU Radio. Thank you for this video. You will get a quick overview of programming the USRP B200 using both LabVIEW and GNU Radio software. For those who want to explore further, please visit our E-InnoVista training page and enroll in our comprehensive training program, where you will receive step-by-step guidance on using LabVIEW and GNU Radio for software-defined radio devices. We have added a training page link in the description sections below. To get more application-based and exciting video like this, don't forget to subscribe and follow our E-InnoVista channel. E-InnoVista, where innovation meets technology. Thank you.